Every night, astronomers point their telescopes toward the constellation Triangulum and witness something impossible. This spiral galaxy, officially catalogued as Messier 33, rotates at speeds that violate everything we know about orbital mechanics. The outer regions move so fast they should fling themselves into the void like water droplets flying off a spinning wheel. Yet here it stands, defiant. The galaxy stretches 60 billion light-years across, containing 40 billion stars arranged in perfect spiral arms. These arms sweep through space in an elegant dance, but the physics behind this dance makes no sense. According to Newton's laws, objects farther from the center should move slower, just like planets in our solar system. Mercury races around the Sun, while distant Neptune crawls along its orbit. But Triangulum breaks these rules. Stars at the galaxy's edge move just as fast as those closer to the center. Some regions even accelerate as they get farther out. It's like watching a cosmic merry-go-round that speeds up the farther you ride from the center. The contradiction puzzled astronomers for decades. What holds Triangulum together? Why hasn't it flown apart? The answer, as shocking as it is invisible, lies in dark matter. Invisible, undetectable directly, but responsible for holding this spinning monster intact. Calculations suggest that 85% of Triangulum's mass isn't visible. It's composed of a mysterious substance that exerts gravity but emits no light. Without dark matter, galaxies like Triangulum wouldn't exist. And yet, the mystery deepens. Within this galaxy, giant blue stars are born at an astonishing rate. These stellar titans, 100 times more massive than our Sun, burn through their fuel in a cosmic blink, just a few million years. Triangulum's arms are littered with these luminous beacons, clustered in massive star nurseries. They shine like cosmic jewels in pinkish nebulae, clouds of hydrogen where gravity works its ancient magic. In places like NGC 604, one of the largest star-forming regions in the local group, thousands of young stars cluster together, their ultraviolet radiation lighting up surrounding gas clouds in glowing pink and purple hues. These nurseries are both cradles and graveyards. The biggest stars live fast and die young, ending in supernovae that seed the galaxy with heavier elements: carbon, oxygen, iron, the building blocks of life. But Triangulum's secrets don't end with stars. Hidden among its spiral arms, astronomers have detected the telltale signs of rogue black holes, dark, drifting predators that were once the hearts of stars. These black holes roam invisibly, bending light and space around them. When they interact with nearby stars or clouds of gas, they reveal their presence through gravitational lensing and X-ray flares. Some theories suggest these black holes might eventually merge, creating gravitational waves we could detect here on Earth. In fact, missions like LIGO and Virgo have already picked up ripples in space-time from galaxies millions of light-years away. What's astonishing is how galaxies like Triangulum can be both chaotic and beautifully ordered. How can a galaxy that spins so fast remain structured for billions of years? The answer may lie in cosmic balance, a tension between dark matter, gravity, star birth, and death. Each element plays a role in an ever-evolving galactic ecosystem. And Triangulum, despite its defiance of Newtonian physics, may be one of the best laboratories we have to understand the grand architecture of the cosmos. As we peer deeper into its spiral arms, with instruments like the Hubble Space Telescope and the James Webb Space Telescope, we find ever more detail. Cold gas filaments feeding star formation, supernova remnants expanding outward, dense molecular clouds in gravitational collapse. Triangulum is alive, a dynamic, spinning archive of cosmic history. And it's just one galaxy among trillions. In this vast universe, Triangulum teaches us that not everything follows the rules. Some galaxies break them, And in doing so, they help us rewrite the book of physics. In the dark corridors of interstellar space, rogue black holes drift like silent submarines in the deep ocean, undetectable, unseen, yet dangerously real. Within the Triangulum Galaxy, these stellar remnants roam freely, the forgotten cores of long-dead stars. Some were born in the galaxy's earliest, most primitive epochs, when metals were rare, and the laws of stellar death created black holes different from any we know today. Others are cosmic refugees, exiled remnants from galactic collisions. When smaller galaxies merged or were devoured by Triangulum in the distant past, powerful tidal forces flung their central black holes outward. Now, these vagabond entities drift through the galaxy's spiral arms, untethered and invisible, until fate aligns them with an unlucky star. And when that happens, the results are apocalyptic. As a rogue black hole approaches a star, its gravity pulls with increasing ferocity. The star stretches, warps, becoming a distorted sphere of plasma under immense tidal strain. If it crosses the event horizon, the point of no return, the star is lost forever. Its matter vanishes into the black hole's core, never to escape again. But sometimes the encounter is more complex. If the star orbits just outside the event horizon, the black hole can rip away its outer layers in a slow and terrifying process called tidal disruption. The star is slowly consumed, not all at once, but in pieces. These events are among the most energetic phenomena in the universe. They emit bursts of X-rays, gamma rays, and even gravitational waves. From millions of light-years away, our instruments can detect these flares like cosmic screams across the void. Astronomers now believe that Triangulum is home to millions of these stellar-sized black holes. Some are ancient, remnants of stars that lived and died before our sun was even born. Others may be younger, formed in recent supernovae in Triangulum's many star-forming regions. But black holes don't just devour, they also shape galaxies. As they feed, they eject jets of material and radiation that can influence star formation. In dense galactic cores, black holes regulate the temperature of surrounding gas, suppressing or triggering bursts of new stars. In rare cases, two black holes may encounter one another. If they spiral inward and merge, they release a titanic shockwave of gravitational energy, enough to shake the very fabric of space-time. In 2015, scientists on Earth detected such a ripple for the first time, and more have followed since, some likely originating in galaxies just like Triangulum. These mergers help us map the hidden population of black holes across the universe. Each wave tells a story of death, fusion, and cosmic rebirth. But not all black holes remain in isolation. Some become binary systems, locked in a deadly embrace with a companion star. As they orbit, the black hole siphons matter from the star, creating an accretion disk, a whirlpool of gas that heats up and glows fiercely in X-rays. These systems are like cosmic lighthouses, beaming signals across the galaxy, and they help scientists study how black holes grow, spin, and evolve. What's most haunting is the silence. Black holes, by their nature, are dark. They emit no light. Unless they interact with something, a star, a gas cloud, another black hole, they remain hidden. That means Triangulum's rogue population could be far greater than we suspect. For every black hole we detect, dozens more may wander unseen. One day, one of them might pass through a dense stellar nursery or brush past a young blue giant, and the galaxy will light up with energy. That's the paradox of black holes. They are both destroyers and creators. Their violence seeds galaxies with heavy elements. Their jets sculpt the interstellar medium. Their mergers help us explore the limits of general relativity. In Triangulum, these predators are part of the ecosystem. Invisible, yes, but vital. As telescopes like James Webb push our vision further into the infrared, we're beginning to see hints of these dark travelers, not just in Triangulum, but in galaxies across the cosmos. Future missions like LISA, Laser Interferometer Space Antenna, will detect gravitational waves from merging black holes in space itself. When that happens, we won't just be looking at rogue black holes, we'll be listening to them, and the universe will speak in ripples. In a galaxy that defies physics, that spins faster than it should, and births star by the thousands, it's the quiet, invisible forces that hold the most power. As we continue our journey through Triangulum, one truth becomes clear. Silence in space doesn't mean peace. Sometimes it means something massive and ancient is moving in the dark. Among the most spectacular stars in the Triangulum Galaxy are the blue supergiants, celestial titans that shine brighter than 100,000 suns, yet live fleeting lives that barely register on cosmic timescales. These stars are nuclear furnaces, fusing atoms with ferocious intensity. At their core, temperatures soar beyond 50 million degrees Celsius, hot enough to forge elements up to iron. Each second, they convert nearly 4 million tons of matter into pure energy, radiating a dazzling blue-white light visible across thousands of light years. Their surface temperatures exceed 40,000 degrees, 7 times hotter than our sun. This is why they glow blue, not just from color, but from sheer heat. Their fierce stellar winds, propelled by this energy, blast off outer layers of gas and dust. If our sun were exposed to these winds, it would be stripped bare in just a few million years. But this brilliance comes at a price. These stars burn through their fuel with reckless abandon. While our sun will last for approximately 10 billion years, a blue supergiant uses up its hydrogen in only 3 to 5 million years. Imagine a water supply. Our sun sips slowly while a blue supergiant opens the floodgates and lets it pour at full force. These stars are fire hoses in a universe of teacups, and when they die, they do so with apocalyptic power. As they exhaust their hydrogen, they begin fusing heavier elements in their core: helium, carbon, oxygen, until they reach iron. At this point, fusion stops yielding energy. The star's core collapses, triggering a supernova, an explosion so powerful it briefly outshines an entire galaxy. In these last moments, matter is crushed into either a neutron star or a black hole. The remnants of their existence ripple through the universe. Their explosions spread elements like calcium, oxygen, and iron, elements that will one day be part of new stars, planets, and even life. These stars are the ultimate recyclers of the universe. Their deaths make life possible. But there's another twist. The sheer size of these stars often causes instability. Even before they explode, blue giants can shed huge layers of their outer envelopes, forming nebulae and shells of gas that drift outward, forming stunning halos. One example in Triangulum is a star surrounded by a bubble of expelled material nearly 60 light-years wide. It's like a dying breath, frozen in time, illuminating the space around it. And it gets stranger. Some of these massive stars don't explode. Instead, they collapse directly into black holes, vanishing without a trace in a process known as failed supernovae. Observing these vanishing stars has become a frontier in astronomy, silent disappearances in a universe that's usually explosive. These blue supergiants are often born in massive star clusters, where gravitational interactions shape their fate. Sometimes, two stars in close orbit can exchange mass or even merge, creating even more massive and volatile giants. Binary systems like this are ticking time bombs. When one goes supernova, it can trigger the collapse or ejection of its companion, hurling stars through space at hundreds of kilometers per second. These runaway stars are often detected speeding through the arms of galaxies, like bullets fired from invisible cosmic guns. In Triangulum, astronomers have detected multiple high-velocity stars, likely born from such violent cosmic divorces. What makes all of this even more mesmerizing is that we are seeing these stars as they were millions of years ago. Because Triangulum is nearly 3 million light-years away, the light from these stars has taken that long to reach us. Many of them may already be gone, collapsed, exploded, or turned into black holes, while we're just now witnessing their former glory. This delayed cosmic message makes every observation a form of time travel. We're not just studying space, we're peering into the universe's past, watching the fireworks from a show that ended eons ago. Yet in this spectacle lies knowledge. Studying these stellar giants helps us understand not only galactic evolution, but also the origins of the very elements that make up our world. In the dance of light and death, blue supergiants are fleeting, fierce, and fundamental. They are the universe's flashbulbs, brief, brilliant, and unforgettable, drifting through the vast darkness of space like ghosts. Rogue black holes are among the most dangerous and least understood objects in the cosmos. In the Triangulum Galaxy, scientists estimate that millions of these invisible wanderers lurk silently between stars, remnants of a violent stellar past. Unlike the black holes that sit at the centers of galaxies or the ones in tight binary systems, rogue black holes travel alone. They don't emit light. They don't pulse. They don't announce their presence. They simply glide through space, quiet, deadly, and almost impossible to detect. Some of them were formed billions of years ago, when the galaxy was still young and rich in massive stars. Others were kicked out of binary systems after supernova explosions, flung away like cosmic debris. And many are the children of galactic collisions. When two galaxies merge, their black holes often get slingshotted into chaotic orbits. A rogue black hole is not a peaceful drifter. When one comes close to a star, the consequences are catastrophic. The black hole's intense gravitational pull begins to stretch the star, pulling it apart in a terrifying display of tidal forces. Like a rubber band stretched to its limit, the star is distorted, its gases drawn into long tendrils spiraling toward the black hole. Sometimes the star crosses a fatal boundary, the event horizon, and is consumed entirely, vanishing into darkness. Other times, the black hole merely grazes the star, stripping away its outer layers in a process known as tidal disruption. These encounters release enormous amounts of energy, lighting up the galaxy with bursts of radiation visible across millions of light-years. We observe them as bright flares in the sky, brief yet powerful, a silent scream from a star being devoured. These black holes aren't just stellar leftovers, they're cosmic predators, and they shape the evolution of galaxies like Triangulum. Every time a rogue black hole consumes matter, it grows, and every time it interacts with gas or stars, it releases energy that can affect the galaxy's structure. It may heat up surrounding gas clouds, halting star formation. Or it may trigger shockwaves that collapse clouds into new stars. Even in isolation, black holes exert power far beyond their size. But the mystery doesn't stop there. In some parts of Triangulum, astronomers have found signs of intermediate mass black holes, hundreds or thousands of times the mass of our Sun. These may have formed from the merging of smaller rogue black holes, creating a new class of objects that straddle the line between stellar black holes and the supermassive ones found in galactic cores. If these mergers continue over time, they may eventually become central black holes themselves. Imagine a galaxy quietly growing a monster in its outskirts without anyone realizing, until it's too late. Today, missions like LIGO and Virgo detect gravitational waves from these black hole collisions. Each ripple in space-time is a message from the invisible, a story of destruction, rebirth, and cosmic transformation. Some of these waves may have come from galaxies like Triangulum, where rogue black holes dance in the dark. What's even more fascinating is how close we are to hearing these cosmic whispers directly from space. In the coming decades, missions like LISA, Laser Interferometer Space Antenna, will orbit the Sun and listen for low-frequency gravitational waves. With it, we may detect even more distant black hole mergers, and possibly witness the silent migration of rogue black holes as they wander across the stars. And while these giants roam Triangulum, the same could be true here in the Milky Way. In fact, scientists believe our galaxy may host thousands, even millions of rogue black holes. Some may even pass close to our solar system, not close enough to destroy us, but enough to subtly distort the orbits of comets and stars. One day, a black hole might pass near a dense star cluster or glide silently through a nebula. And when it does, the skies may erupt in X-rays and gravitational waves, revealing its presence only through the destruction it leaves behind. But even now, these silent killers continue their slow march across the galaxy, warping space, bending time, and hiding in plain sight. They are not just cosmic threats, they are cosmic storytellers. They carry the history of ancient stars, the scars of galactic mergers, and the seeds of new cosmic formations. They are the echoes of death and the catalysts of rebirth. In a universe where most things shine, rogue black holes remind us that power can lie in silence. So the next time we look up into the night sky and see only stars, remember, in the vast darkness between them, something ancient and invisible might be passing right by. Deep within the arms of the Triangulum Galaxy, colossal blue stars ignite with ferocity and brilliance, unmatched by nearly any other object in the cosmos. These are the blue supergiants, the largest, hottest, and most short-lived stars in the universe. They are magnificent to behold. Their surfaces blaze at temperatures exceeding 40,000 degrees Celsius, nearly 7 times hotter than our Sun. This immense heat gives them their signature blue-white hue, a color that marks the peak of stellar temperature and energy output. But beauty comes at a cost. These titans are living on the edge. A blue supergiant consumes its nuclear fuel at breakneck speed, converting nearly 4 million tons of matter into energy every second. Deep in their cores, temperatures soar past 50 million degrees Celsius, enough to fuse hydrogen into helium, then into heavier elements like carbon, oxygen, and eventually iron. But once they reach iron, the chain reaction stops. Fusion no longer produces energy, and the star begins to die. Unlike our Sun, which will quietly fade into a white dwarf after billions of years, a blue supergiant has no such graceful exit. Their entire existence is a race toward oblivion. While the Sun lives for 10 billion years, blue supergiants survive for only 3 to 5 million years. A blink in cosmic time. Imagine a candle burning with such intensity that it consumes itself in minutes rather than hours. That is the fate of these stellar giants. As they near the end of their short lives, their outer layers become unstable. Waves of gas erupt from their surfaces, carried away by powerful stellar winds. These winds are so strong they could strip away the entire mass of a star like our Sun in just a few million years. What remains is a bloated, unstable core, a time bomb ticking toward detonation. And then, in one final violent moment, the star collapses inward and explodes outward in a supernova. These explosions are among the most powerful forces in the universe. A single supernova can outshine an entire galaxy for days or weeks. It blasts heavy elements into surrounding space, seeding nearby nebulae with the building blocks of planets, oceans, and life. In a very real way, everything we are, every atom in your body, was forged in the heart of a star like this. But not all blue supergiants explode in visible ways. Some may collapse directly into black holes, vanishing from view without a sound. These failed supernovae are difficult to observe, but astronomers are now monitoring certain stars that have mysteriously disappeared, hoping to catch one of these silent deaths in real time. One such candidate lies within the Triangulum Galaxy. A massive star, once catalogued and photographed, has vanished without a trace. It didn't brighten. It didn't explode. It simply went dark. And perhaps that's the most haunting truth about blue supergiants. For all their brilliance and fury, their final moments can be both earth-shaking and invisible. These stars don't live alone. Many exist in binary systems, locked in gravitational orbits with a companion star. In some cases, the interaction is dramatic. One star siphons material from the other, leading to wild flares, mass ejections, or premature death. In even rarer cases, the two stars merge, forming a new hypergiant, even more massive, even more unstable. These stellar duels are not peaceful. When one goes supernova, the explosion can kick the surviving companion out of orbit, flinging it through the galaxy at hundreds of kilometers per second. These are known as runaway stars, and some are detected hurtling through space from past celestial catastrophes. We've found them in Triangulum, stars traveling faster than anything else around them. Each is a smoking gun, evidence of a supernova long past. And all of this, the fire, the fury, the speed, the destruction, it all happens in a tiny sliver of cosmic time. The entire lifespan of a blue supergiant is shorter than the time it takes light to cross the Milky Way. Yet in that brief existence, these stars change the galaxy around them. They carve out vast ionized nebulae, heat nearby gas, and influence the birth of new stars. They are both destroyers and creators, a reminder that even the most unstable things in the universe can have lasting impact. When we look at these stars through telescopes like Hubble and James Webb, we are seeing their past. Their light has taken millions of years to reach us. Some of them may have already exploded or disappeared, while their light continues to travel. Watching a blue supergiant is like watching a memory from deep time. It's a glimpse of a universe always in motion, always transforming. And in that glimpse, we find a reflection of our own fragile brilliance, a reminder that even the brightest lights burn out fast, but their echoes can last forever. At first glance, the Triangulum Galaxy appears to be a simple, elegant spiral, a textbook example of galactic symmetry. Two sweeping arms curl gracefully from its center, adorned with star clusters, nebulae, and young blue suns. But look closer, and the simplicity begins to unravel. Recent high-resolution observations have revealed something unexpected. Triangulum's spiral arms aren't perfectly uniform. Instead, they twist, branch, and ripple with surprising complexity. In several regions, spur-like structures branch off from the main arms, forming twisted lanes of gas and stars that defy the traditional models of spiral formation. Some spiral arms even appear to split and reconnect, like strands of a living organism reacting to forces we can't fully see. These features aren't random. They may be caused by local gravitational instabilities, where massive star-forming regions tug on the galaxy's fabric, or by shock waves traveling through the galactic disk. Think of the galaxy not as a rigid pinwheel, but as a dynamic, breathing structure, constantly reshaping itself in response to internal and external forces. Understanding how spiral arms evolve isn't just an academic exercise. It's a window into the very physics of galactic life. The patterns in a galaxy's arms tell a story of gas flows, star birth, gravitational waves, and even ancient collisions. In the case of Triangulum, Scientists believe these spur structures could represent temporary formations, the result of massive molecular clouds pushing their way through the disk and triggering waves of star formation. In some cases, these spurs become hotbeds of stellar birth. When gas is compressed along the edges of a spiral arm or spur, gravity takes over, pulling atoms together until stars ignite. That's why so many of Triangulum's young, luminous stars cluster in these complex regions. But the deeper mystery lies not in the arms, but at the center, in the galactic core. Here, the spiral symmetry gives way to chaos. The very heart of the Triangulum Galaxy is a region of extraordinary density. Stars are packed more tightly than anywhere else in the galaxy. The rules of motion change. The orbits of stars become unpredictable, warped by the intense gravitational pull of massive objects, possibly even a central black hole. Unlike the Milky Way, which harbors a confirmed supermassive black hole at its core, Triangulum remains an open question. Some studies suggest the core is too diffuse to host a massive black hole. Others point to faint X-ray emissions and velocity anomalies as signs of a hidden monster lurking in the shadows. If Triangulum does harbor a central black hole, it would reshape our understanding of how galaxies like it form and evolve. Perhaps it is still growing. Perhaps it's smaller than expected. Or perhaps something else entirely is driving the dynamics of its core. One thing is certain: the galactic center holds clues to the galaxy's past. It may contain stars that formed during the very first wave of starburst activity. It may also hold remnants of smaller galaxies consumed in past mergers, their cores buried deep within the spiral's heart. And just like the spiral arms, this region is not static. It pulsates with motion. Stars orbiting in elliptical loops, clouds of gas colliding and spinning inward, bursts of radiation flickering like cosmic heartbeats. Triangulum's spiral design is not just beautiful, it is a record of cosmic evolution. Each arm, each spur, each ripple in the galactic disk is the result of billions of years of gravitational tension and release. And the lessons we learn from it ripple outward too. By understanding how arms form in Triangulum, we gain insights into more distant galaxies, those billions of light-years away whose faint spirals we can barely resolve. Galactic spirals are not decorative. They are maps of momentum, blueprints of birth, and records of the gravitational symphony that shapes the universe. So as we continue to observe and simulate galaxies like Triangulum, we are not merely admiring their form. We are decoding their function, discovering how a spiral becomes a cradle for stars, a mirror of dark matter, and a fingerprint of time. And at the center of it all, hidden beneath the swirling arms and luminous clouds, lies a secret that may change everything we know about galaxies. Waiting, as always, in the dark. In the glowing arms of the Triangulum Galaxy lie the most intense and crowded star-forming regions in the cosmos, colossal stellar megacities where blue and white supergiants blaze side by side in radiant fury. These stars are monsters, reaching surface temperatures above 50 degrees Celsius, emitting energy at levels the human mind can barely comprehend. A single cluster can outshine 100 million suns, releasing so much radiation that it literally sculpts space, blasting away surrounding gas and carving vast voids in the interstellar medium. These cavities are not silent. They are battlefields. Within them, pressure builds. Shock waves collide. Gas is compressed. And like dominoes, these forces trigger the formation of even more stars. A chain reaction of stellar birth set off by the violence of earlier generations. But this beauty is fleeting. Massive stars live fast and die violently. Within just a few million years, the blink of a cosmic eye, these giants burn out, often in brilliant supernova explosions that further reshape their environment. Their deaths are not the end, but the beginning of a new transformation. These clusters evolve, not just in brightness, but in structure. Over time, something remarkable happens inside them, a process called mass segregation. As stars interact gravitationally, the most massive ones gradually migrate toward the cluster's center. Like heavyweight champions taking the central ring, they push smaller stars outward. The result is a gravitational hierarchy, a luminous core of giants surrounded by a halo of smaller, cooler stars. It's not just a visual spectacle, it's physics at work on an unimaginable scale. In the densest clusters, stars are so close together that interactions happen constantly. Some systems form binary stars, two suns locked in a gravitational embrace. Others may merge, giving birth to hypergiant stars or even the seeds of future black holes. These environments are also rich in high-energy phenomena. X-ray binaries, neutron stars, and exotic objects like millisecond pulsars thrive here. In some cases, astronomers suspect the presence of intermediate-mass black holes, invisible giants lurking at the centers of particularly massive clusters. These stellar cities are not permanent fixtures in the galaxy. They are transient, constantly evolving, dissolving, and reforming. The gravitational pull from the Triangulum Galaxy itself gradually pulls them apart. Over hundreds of millions of years, the clusters lose mass, shed stars, and disperse into the broader galactic disk. But their legacy remains. The stars they formed, the metals they forged, the shockwaves they triggered. Every supernova enriched the interstellar medium with elements like carbon, oxygen, and iron, the very ingredients of planets, oceans, and life itself. Without them, galaxies would be barren. In many ways, these clusters are the furnaces of creation. One of the most famous in Triangulum is NGC 604, a vast stellar nursery spanning nearly 1,500 light-years. It contains over 200 massive stars, each more than 20 times the mass of our Sun. This one region alone is a galactic beacon, visible across the local group of galaxies. When astronomers peer into NGC 604 with instruments like the Hubble Space Telescope or the James Webb Space Telescope, they don't just see stars. They see time, motion, and transformation frozen in the act. They see raw power and delicate balance, chaos and creation, and they see a reflection of the cosmic cycle that builds galaxies, shapes planets, and eventually makes life possible. What's even more intriguing is how similar these processes are to those in other galaxies. By studying star clusters in Triangulum, we gain a universal blueprint for how stars are born in spiral arms everywhere. Whether in Andromeda, the Milky Way, or distant galaxies a billion light-years away, stellar megacities follow similar rules. Dense gas clouds collapse, stars form in clusters, mass segregation reshapes structure, supernovae clear the way, and new stars rise from the ashes. It is a self-sustaining rhythm, a cosmic heartbeat that echoes throughout the universe. So the next time you see a glowing patch in the arm of a galaxy, whether in an image from NASA or a sci-fi movie, know that it's more than a pretty light. It's a city of giants, a cathedral of fire, a place where stars are born, live like gods, and die in glory. And out of that glory comes everything else. Across the vast expanse of the Triangulum Galaxy, millions of stars are locked in a silent, spinning duet, performing a gravitational ballet that, while elegant and seemingly eternal, often ends in spectacular destruction. These are the binary star systems, pairs of stars born together, bound forever by the invisible pull of gravity. More than half of all stars in the universe, including those in Triangulum, are part of such unions. Some pairs orbit peacefully for billions of years, their paths stable and serene. Others are on a slow spiral toward catastrophe. Every binary system is unique. Some feature stars of nearly equal mass, orbiting a shared center in perfect balance. Others are unevenly matched, one large and dominant, the other smaller and subservient. But all binaries share a delicate gravitational relationship. Over time, however, stellar evolution begins to shift that balance. In systems where one star is significantly more massive than its companion, the larger star evolves much faster. It burns through its nuclear fuel quickly and swells into a red giant, its outer layers ballooning outward like a dying ember flaring for one last breath. As it expands, its surface may cross a dangerous boundary, the Roche lobe, where the gravitational pull of the companion star becomes stronger than the red giant's own. At that point, matter begins to flow from the giant to the smaller star in a process called mass transfer. This dramatic shift can change everything. The companion star begins to swell with new material. Its brightness may surge. It may erupt in nova outbursts as it struggles to absorb the sudden flood. If the system survives this phase, the red giant may eventually collapse into a white dwarf, leaving behind a dense stellar core still locked in orbit. But the drama doesn't end there. If the white dwarf continues to pull mass from its companion, it can reach a critical limit, known as the Chandrasekhar limit, and ignite in a catastrophic Type Ia supernova. These explosions are some of the brightest events in the universe, and are used by astronomers as cosmic yardsticks to measure the expansion of space itself. Other binary fates are even more extreme. In some systems, both stars are massive enough to end their lives as neutron stars or even black holes. After billions of years, gravitational radiation causes their orbits to decay. They spiral inward slowly, until one day they collide. The result? A violent merger that emits a burst of gravitational waves, ripples in the very fabric of space-time, along with high-energy radiation and possibly even heavy elements like gold and platinum, forged in the fire of collision. These events, once purely theoretical, are now being observed in real time by instruments like LIGO and Virgo. In fact, one such neutron star collision was detected in 2017, producing not only gravitational waves but visible light and gamma rays, a cosmic multi-messenger event that reshaped our understanding of stellar death. Back in Triangulum, astronomers have cataloged thousands of binary systems at various stages in their life cycle. Some are just beginning their dance, two young stars glowing side by side in a cradle of gas. Others are older, with one partner already evolved, transferring mass in luminous arcs of material. A few may be in their final acts, slowly spiraling toward one another in silence, their fates sealed. What makes these stories so haunting is how intimate and destructive they are. Binary stars don't just coexist. They interact, influence, distort, and often destroy one another. Their gravitational love story is as poetic as it is perilous. In some systems, the smaller star eventually outlives its giant companion, only to find itself orbiting the dense corpse of its partner, a white dwarf, neutron star, or black hole. In rare cases, the surviving star is eventually consumed as well, falling into the abyss after millions of years. And in other systems, the stars merge entirely, forming a single, more massive and unstable star that burns with renewed fury, only to die more quickly in a supernova or collapse. These are not rare anomalies. They are fundamental parts of stellar evolution. Without binary systems, we wouldn't fully understand how stars change, how elements are formed, or how gravitational waves are generated. Every violent ending tells a deeper truth about how the universe works. Binary stars are not just systems, they are cosmic relationships, sometimes harmonious, often volatile, always transformative. And their echoes, in the form of radiation, light, and gravity, ripple across the galaxy, reminding us that even in space, The most beautiful dances are sometimes the most tragic. In the final stages of a sun-like star's life, something extraordinary happens. The star, no longer able to sustain nuclear fusion in its core, sheds its outer layers into space. What remains is a faint, dense white dwarf, a stellar ghost. But surrounding it, suspended in time, is a glowing shell of gas, a planetary nebula. These nebulae are among the most stunning sights in the Triangulum Galaxy. Seen through powerful telescopes, they resemble floating blossoms, delicate bubbles, or radiant cosmic butterflies. But don't let their beauty fool you. These are the death shrouds of stars, the final exhalations of suns that have run out of fuel. The expanding gas glows in different colors depending on its composition and density. Ionized oxygen often appears greenish-blue. Hydrogen glows red. Sulfur adds orange hues. Together, they form vibrant palettes that trace shock fronts, cavities, and knots of gas. These structures aren't static. In fact, some planetary nebulae evolve visibly over just a few decades. Using time-lapse imagery, astronomers have been able to watch the faint tendrils of gas move, fade, and shift. Cavities grow, lobes expand, regions brighten, then disappear, like brushstrokes on a cosmic canvas being painted and erased in real time. The motion is driven by the powerful stellar winds emitted during the star's red giant phase. These winds carve hollow spheres, or bipolar lobes, depending on the geometry and dynamics of the star's final outbursts. Some of the most fascinating nebulae exhibit symmetry, so perfect it seems deliberate. Bipolar jets, concentric rings, spirals. What causes this celestial architecture? The answer may lie not in the dying star alone, but in a companion star. Many planetary nebulae are formed in binary systems, where a second star orbits the one nearing death. As the primary star swells, the gravity of the companion begins to shape the outflowing gas. Jets of material may be funneled along the orbital plane, punching through the gas and forming hourglass shapes or butterfly wings. In other cases, the gravitational interaction creates spirals, as the gas is shaped by the orbital path of the stars. It's like watching a duet where one dancer is collapsing and the other continues the choreography, leaving trails of motion behind. And these shapes aren't just artistic, they carry physical meaning. By analyzing the structure and motion of nebulae, astronomers can determine the mass loss rate of the dying star, the speed of ejection, and even the timing of each outburst. Each nebula is a record of stellar death written in light and gas. Yet for all their glory, planetary nebulae are fleeting. They last only 10,000 to 50,000 years, a heartbeat in galactic terms. Eventually, the gas disperses into the interstellar medium, enriching it with heavier elements and paving the way for new generations of stars. The white dwarf at the center continues to cool, eventually fading into darkness. All that remains is the legacy, the nebula's contribution to the galaxy's chemistry and beauty. Some of these nebulae in Triangulum are so large and luminous that they can be observed from Earth-based telescopes, despite being nearly 3 million light-years away. They offer scientists a chance to compare stellar deaths across galaxies, to see how factors like metallicity, environment, and stellar companions influence the shape and lifespan of planetary nebulae. And more than that, they offer a spiritual perspective. These dying stars don't go quietly. They leave beauty behind. In their final act, they light up the galaxy with color, geometry, and motion. A farewell performance that contributes to the cycle of cosmic renewal. It's poetic, really. A star spends billions of years generating light and warmth, and when its time comes, it doesn't vanish into nothing. It explodes into art, painting space with remnants of its essence. From chaos comes symmetry. From death comes creation. From silence comes color. And long after the gas fades, the universe remembers. Because every atom in your body, the oxygen in your lungs, the carbon in your cells, the calcium in your bones, was once part of a dying star's last breath. In a sense, you are a nebula reborn. Not all stars are born to stand alone. In the vast, cold arms of the Triangulum Galaxy, many stars begin their lives as part of open clusters, loose associations of stars formed from the same molecular cloud. They are stellar siblings, born together, glowing together. But unlike the ancient, tightly bound globular clusters that orbit far from the galactic core, these open clusters are fragile families, held together by weak gravitational bonds. And like all fragile things, they don't last. From the moment they're born, they begin to fall apart. The most massive stars in the cluster sink toward the center, thanks to gravitational interactions, a process known as mass segregation. These giants burn fast and die young, often exploding in spectacular supernovae that don't just light up the sky, they shatter the delicate balance of the entire cluster. Each stellar death removes mass from the system and destabilizes its gravitational hold. But nature isn't done yet. As the cluster orbits the galactic center, it faces tidal forces from the gravity of the galaxy itself. These forces stretch and distort the cluster, slowly pulling stars away, like threads unraveling from a woven tapestry. Over time, stars are lost one by one, drifting into the wider galaxy. What began as a family becomes a dispersed diaspora of lone travelers, former siblings now separated by thousands of light years. The process is known as cluster dissolution, and it's as inevitable as it is tragic. Most open clusters only survive for a few 100 million years before fading completely. And yet, during that time, they play a critical role in galactic evolution. Because from these clusters emerge not just stars, but solar systems. Planets form around many of these young suns, including rocky worlds, gas giants, and icy exoplanets. Even our own sun is thought to have been born in an open cluster, long since dissolved. Somewhere out there, its long-lost siblings may still shine, their shared origin betrayed only by subtle chemical fingerprints in their atmospheres. Thanks to spectroscopic analysis, astronomers are now able to chemically tag stars and identify those that may have originated from the same cluster, even if they're now scattered across the galaxy. This field, known as galactic archaeology, is helping us reconstruct the history of the Milky Way, and by extension, galaxies like Triangulum. In Triangulum, astronomers have discovered dozens of open clusters at various stages of life. Some are still tightly grouped, glowing with bright blue and white stars, nestled in dusty stellar nurseries. Others are barely distinguishable, their members already drifting away, no longer gravitationally bound. Observing these clusters across time gives scientists a natural laboratory for studying stellar evolution, star formation, and the mechanics of gravitational disruption. Each cluster tells a story, a beginning in a cloud of collapsing gas, a youth filled with brightness and chaos, a midlife shaken by supernovae and shifting orbits, and an end, and as the stars move on, alone into the darkness. There's something deeply human about these stories. Clusters are born, they grow, they break apart, and their legacy lives on, in the stars that remain, and in the planets they may one day nurture. For every open cluster that dissolves in Triangulum, the galaxy gains hundreds of new stars, free agents, now part of the galactic population. Some will migrate toward the core, others will remain in the disk. A few may even be ejected from the galaxy entirely, sent hurtling into intergalactic space. But none of them forget where they came from, their chemical signatures, their velocities, their orbits. These are the clues that help astronomers trace their lineage, piece by piece, like reconstructing a cosmic family tree. And while open clusters may be short-lived, their influence is lasting. The nebulae they illuminate, the elements they scatter, the solar systems they host. All of it contributes to the chemical richness, the diversity, and the dynamism of the galaxy. In the Triangulum Galaxy, these stellar families may not last forever, but what they leave behind helps shape everything that follows. The Triangulum Galaxy is a vast system of stars, gas, and dark matter. But hidden beneath its shimmering surface is a cosmic ocean of invisible forces, quietly shaping everything we see. Among these forces, galactic magnetic fields are some of the most mysterious and powerful. They thread through the interstellar medium like unseen rivers, creating invisible highways for charged particles and subtly steering the motion of gas across vast distances. Though we cannot see them directly, their influence is immense. These magnetic fields accelerate particles to near the speed of light, generating the cosmic rays that constantly bombard every part of the galaxy, including Earth. These high-energy particles carry information about supernovae, stellar winds, and exotic cosmic phenomena. At the same time, these fields guide filamentary structures within the galaxy, long, thread-like strands of gas and dust that stretch across light years, linking distant star-forming regions. The interstellar medium, the space between the stars, is not empty. It's filled with a complex mixture of gas, dust, radiation, and plasma. And this environment is constantly changing, energized by multiple sources. Radiation from stars, cosmic rays, and even the residual light of the cosmic microwave background fill this medium. Together, they form a radiation field that influences chemistry, temperature, and structure. This radiation ionizes atoms, dissociates molecules, and drives the chemical reactions that give rise to complex organic compounds, the building blocks of life. In the densest regions of the interstellar medium, radiation is absorbed by tiny dust grains and re-emitted at longer wavelengths, creating a rich interplay between energy and matter. Though dust makes up only 1% of the interstellar medium by mass, its importance cannot be overstated. These microscopic particles, often smaller than the wavelength of visible light, are composed of silicates, carbon, ices, and metals. Dust grains serve as catalysts for chemistry. On their surfaces, hydrogen atoms meet and form molecular hydrogen, the most abundant molecule in the universe. Other complex molecules like water, ammonia, and even organic compounds can form in these environments. Dust also regulates temperature by absorbing and radiating heat, shielding molecular clouds from harsh starlight, and creating cold pockets where stars can form. And perhaps most poetically, dust grains scatter light, giving rise to the beautiful nebulae we see in deep space photographs, glowing with the colors of ionized gas and illuminated by nearby stars. But this environment is not passive. As massive stars ignite and explode, they inject energy into the interstellar medium, creating shock waves that compress and heat the gas. Supernova remnants can sweep up vast regions of dust and gas, shaping bubbles and cavities that ripple outward for hundreds of light years. This feedback loop, stars forming, dying, and reshaping their surroundings, is one of the most important processes in galaxy evolution. In Triangulum, astronomers have observed shells, arcs, and filaments formed by these energetic events. Many of these structures are aligned with the galaxy's magnetic field, showing just how interconnected gravity, gas, and magnetism really are. Studying these environments is challenging. We can't see magnetic fields or radiation directly. But through radio astronomy, polarization mapping, and infrared observations, scientists can trace their influence. Missions like Planck, ALMA, and the James Webb Space Telescope are helping us uncover the secrets of these invisible forces, revealing how they guide the dance of creation across the cosmos. And all of this, magnetic fields, radiation, dust, cosmic rays, is happening at once, constantly, quietly, behind the scenes. The stars may get the spotlight, but the stage on which they shine is just as fascinating. It's easy to forget that space is more than emptiness. It's alive with motion. It hums with energy. It glows with ancient light and vibrates with the echoes of stellar explosions. And in that interplay of the seen and unseen, galaxies like Triangulum take shape. They grow, they evolve, they produce life-giving elements, and maybe even life itself. So the next time you look at an image of a galaxy, think not just of the stars and spiral arms, but of the invisible framework that binds it all together. The magnetic threads, the radiation fields, the grains of dust drifting between the stars. Because it's in those hidden spaces that the future of the universe is written. The galaxy is not just a collection of stars and gas. It's a living ecosystem where invisible forces regulate the birth of stars, the flow of matter, and possibly even the evolution of life. At the heart of this invisible machinery is something almost impossibly delicate: the galactic magnetic field. It threads through every cubic centimeter of the Triangulum Galaxy, forming a vast and elegant electromagnetic scaffold that shapes everything it touches. Though incredibly faint, nearly 1 million times weaker than Earth's magnetic field, this force stretches across tens of thousands of light-years, influencing cosmic rays, star formation, gas dynamics, and even planetary environments. It's like a nervous system for the galaxy, a silent network of power and control pulsing with electromagnetic energy. These magnetic field lines trace the shape of the galaxy's spiral arms, flowing in long, curving patterns that echo the architecture of visible stars and nebulae. Where the spiral arms twist, so do the magnetic lines, elegantly aligned in a dance that connects regions separated by unimaginable distances. But this structure doesn't just look beautiful, it does work. It channels cosmic rays, those high-energy particles born from supernovae and extreme environments. Instead of flying aimlessly, these particles travel along invisible tracks formed by magnetic fields. In doing so, they interact with the interstellar medium, depositing energy, driving chemical reactions, and even influencing the ionization of planetary atmospheres. In fact, some scientists speculate that changes in galactic magnetic fields over millions of years could affect biological evolution on habitable worlds, possibly even Earth-like planets orbiting distant stars. Imagine it: invisible waves of energy, pulsing across space, shaping not just the stars, but the potential for life. The magnetic field also regulates star formation. In dense molecular clouds, the birthplaces of stars, magnetic pressure helps balance gravity, slowing down the collapse of gas and influencing where and when stars ignite. Without this balancing force, clouds might collapse too quickly or chaotically, leading to bursts of unstable formation. In this way, magnetism introduces order into cosmic chaos, and the complexity doesn't end there. The field itself is shaped by galactic rotation and dynamo processes, mechanisms that convert the motion of conducting plasma into organized magnetic energy. Over millions of years, this dynamo acts like a cosmic generator, amplifying and sustaining the magnetic field of the entire galaxy. It's a feedback loop of movement and magnetism. Stars rotate, gas flows, plasma spins, magnetism rises. And through this interaction, the galaxy becomes more than just a disk of matter. It becomes an electromagnetic organism, interconnected, pulsing, alive. In the Triangulum Galaxy, astronomers have used radio polarization maps to trace these field lines. They reveal elegant curves, long filaments, and regions where magnetism aligns with galactic motion. These maps are not just beautiful, they're diagnostic. They allow scientists to measure field strength, coherence, and orientation. Some regions show highly ordered fields that stretch for thousands of light years. Others appear chaotic, shaped by nearby supernovae or turbulent gas flows. This patchwork of order and chaos mirrors the dual nature of the galaxy itself, structured yet dynamic, predictable yet surprising. Understanding galactic magnetism isn't just about theory. It helps explain real phenomena: why some star-forming regions are more productive than others, how cosmic rays reach planetary systems, how the interstellar medium maintains its structure. It also hints at a deeper truth, that the forces we cannot see may be just as important as those we can. For centuries, humans have looked at galaxies and seen light. But in truth, galaxies are more than that. They are webs of invisible power, electrical, magnetic, gravitational, all working in concert to create the cosmos. And the magnetic field may be the quietest and most profound of them all. It does not shine. It does not roar. But it reaches across space, touches every star, and holds the galaxy together in ways we are only beginning to understand. So the next time you look at an image of the Triangulum Galaxy, its graceful arms and glowing core, remember, beneath that beauty lies something deeper: a nervous system, a field of influence, a structure of silence that connects everything to everything else. Everything we've explored so far, stars, clusters, nebulae, supernovae, black holes, represents just a tiny fraction of what actually exists in the Triangulum Galaxy. The visible parts of the galaxy are merely the tip of a cosmic iceberg. The majority of Triangulum's mass, possibly over 85%, is completely invisible, detectable only through its gravitational pull on stars and gas. This profound mystery has haunted astrophysicists for decades, and it raises one of the most important questions in modern science: what is the universe really made of? There are three main possibilities that scientists have proposed to explain this discrepancy. The first possibility is bold: that our understanding of gravity is incomplete or fundamentally flawed. Perhaps Newton's and even Einstein's theories break down when applied to galactic scales. Some physicists have proposed alternative models, such as Mond-Sol, modified Newtonian dynamics, where the laws of motion change at very low accelerations. These models attempt to explain why galaxies like Triangulum spin faster than they should without flying apart, all without invoking invisible matter. But there's a problem. While modified gravity can explain some rotation curves, it struggles with others. It fails to account for large-scale cosmic structures, gravitational lensing patterns, and especially the fluctuations observed in the cosmic microwave background. In short, these theories offer partial solutions, but leave many questions unanswered. The second possibility is more conservative. Maybe the galaxy is filled with ordinary matter that we simply can't see. This includes brown dwarfs, failed stars that never ignited fusion, black holes which emit no light, or massive cold molecular clouds made of hydrogen too cool to radiate. For a time, this seemed promising. If enough of these dark objects existed, perhaps they could account for the missing mass. But despite decades of surveys, including deep observations in infrared and radio wavelengths, scientists haven't found nearly enough of these objects to explain the discrepancy. The numbers don't add up. That brings us to the third possibility, and the current leading explanation: dark matter, a mysterious, exotic form of matter that doesn't emit or absorb light. It interacts only through gravity, making it completely invisible, yet unmistakably real in its effects. In this model, the Triangulum Galaxy is embedded in a vast halo of dark matter, a ghostly sphere that extends well beyond its visible boundaries. This halo acts like a gravitational shell, holding the galaxy together and explaining why stars at the edges orbit as fast as those near the center. Dark matter also helps explain why galaxies formed in the first place. In the early universe, slight fluctuations in density grew under the influence of dark matter, forming the cosmic web of filaments and clusters we observe today. Without it, the universe as we know it might never have taken shape. But what is dark matter made of? That question remains unanswered. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that interact via gravity and the weak nuclear force. Another contender is the axion, an ultralight particle that may behave more like a field than a particle. Some scientists propose sterile neutrinos, or even primordial black holes left over from the Big Bang. Yet despite massive efforts, from underground detectors like Xenon-NT to particle accelerators like the Large Hadron Collider, no confirmed dark matter particle has ever been detected. It's frustrating and fascinating, because it means that we live in a universe where most of the matter is invisible, and we still don't know what it is. In Triangulum, as in most spiral galaxies, dark matter is not a footnote. It is the main structure, the silent skeleton that shapes the galaxy's behavior. It influences the orbits of stars, the flow of gas, the formation of clusters, and possibly even the trajectory of satellite galaxies. And yet, we see none of it directly. It's a reminder that perception is not reality, that the universe hides more than it reveals. But perhaps that's the beauty of it. The hunt for dark matter is not just a scientific quest, it's a philosophical one, a search for something beyond the light, something that connects what we know to what we don't. And in that space, between mystery and understanding, galaxies like Triangulum continue to spin. Unseen, unbroken, unanswered. The stars we see today, blazing, swirling, orbiting, are not just celestial ornaments. They are the children of ancient cosmic clouds, formed through an intricate ballet of gravity, chemistry, and time. Deep within the spiral arms of the Triangulum Galaxy, giant molecular clouds drift through space like colossal ghosts, silent, cold, and full of potential. These clouds contain enough material to create millions of stars, yet for millions of years, they remain stable. The pressure inside, caused by random thermal motion of molecules, perfectly balances the inward pull of gravity. It's a fragile piece, like a boulder perched on a ledge, waiting until something pushes it over the edge. And that trigger often comes from beyond. A shock wave from a nearby supernova explosion, the pressure front from a neighboring stellar wind, the gravitational nudges of spiral arm density waves. Once disturbed, the balance collapses. The cloud begins to contract, slowly at first, then with accelerating speed. Denser regions form inside, pockets of material where gravity dominates. These pockets become protostars. As they collapse, gravitational energy is converted into heat. The core grows hotter and denser until, at around 10 million Kelvin, hydrogen nuclei begin to fuse into helium. A new star is born. Light floods into the darkness. But this process doesn't happen in isolation. Stars rarely form alone. Dozens, hundreds, even thousands of stars can ignite simultaneously in a single collapsing cloud, giving rise to stellar nurseries like the Orion Nebula in our own galaxy, or even denser clusters in Triangulum. In these environments, young stars burn hot and fast. Their radiation and stellar winds carve out vast bubbles in the surrounding gas, pushing back the very clouds that form them. These feedback mechanisms are violent and dramatic, yet they're also vital. They regulate star formation, preventing clouds from collapsing too quickly or chaotically. They seed the galaxy with heavy elements, forged in stellar cores and distributed through space when these stars die in supernovae. They create diversity in star mass, temperature, and chemical composition. In Triangulum, astronomers have identified multiple active star-forming regions, some glowing with hot, young stars barely a few million years old. Through infrared telescopes, scientists can peer into the dust and observe the very first stages of stellar birth. When protostars are still wrapped in gas, their light dimmed by cosmic veils. These early stars spin rapidly, accreting material from a rotating disk of gas and dust. And within these disks, something extraordinary begins to happen. Planets form. Tiny grains of dust collide, stick, and grow into pebbles, rocks, planetesimals. Some of these merge into terrestrial planets. Others gather gas to become gas giants. Every star born in Triangulum carries the potential not just for light, but for life. That's the true miracle of star formation. It's not just about creating suns. It's about creating the conditions in which life-sustaining worlds might arise. Yet not all stars survive their infancy. Some are ejected from their clusters due to gravitational interactions. Others accrete too much material and collapse into brown dwarfs or fail to ignite at all. Star formation is a chaotic, competitive process. Only the most stable cores ignite fusion. Only a fraction of those will live long enough to form complex planetary systems. But out of this chaos emerges order. From turbulence comes structure. From collapse comes creation. The Triangulum Galaxy is a living testament to this balance. A galaxy where stars are constantly dying and being born. A galaxy forever creating itself. One cloud, one star, one supernova at a time. In this grand cycle, the universe recycles its elements, its energy, and perhaps even its potential for life. So when you look up at the night sky and you see a single twinkling point of light, remember, that light began its journey in a dark, cold cloud, pushed into brilliance by a shockwave from a long-dead star. The story of one star is the story of many, and the story of how the universe gives birth to itself. Death and birth are not opposites in the cosmos. They are partners in a continuous cycle. Nowhere is this more evident than in a process known as triggered star formation. A single supernova, the cataclysmic explosion marking the death of a massive star, can unleash energy across hundreds of light years, igniting a cascade of new star births in its wake. Imagine a dying star sending out shockwaves, like ripples in a galactic pond. These shockwaves compress vast regions of the interstellar medium, pushing loose clouds of gas and dust into tight, dense pockets primed for collapse. This is not random chaos. This is orchestrated regeneration. These compressed regions soon become new molecular clouds, where gravitational collapse begins. Protostars ignite, planets begin to form, and a new generation of stars emerges, all born from the violent death of a single ancestor. In this sense, every new star is a tribute to the one that came before it, a legacy written in light. But the shockwaves don't stop at mere compression. As they sweep outward, they collect additional material from the diffuse interstellar gas, sweeping it together like cosmic snowplows. These dense ridges of swept-up matter form new clouds where no clouds existed before, expanding the galaxy's capacity for star formation and seeding life into previously barren corners of space. Even more remarkable is the chemical enrichment these explosions provide. The shockwave doesn't just carry energy, it carries the heaviest elements in the universe: carbon, oxygen, silicon, iron, all forged in the dying star's core and ejected into space during its final, fiery breath. These elements mix with the newly forming clouds, enriching them and increasing the chance of rocky planets, atmospheres, oceans, and perhaps life itself. So, the death of a star isn't just a moment of destruction. It's a catalyst for creation, an artist's hand that paints new worlds into being with the ashes of the old. In the Triangulum Galaxy, regions affected by triggered star formation appear as glowing shells and arcs, huge curved structures of ionized gas surrounding dead stellar cores. Through telescopes like ALMA and James Webb, astronomers can observe these shells in incredible detail, watching the way gas flows, dust collects, and stars ignite. In some regions, entire star clusters have been born from the wake of a single supernova. This domino effect of stellar birth can continue for millions of years, as each generation of stars eventually creates new shockwaves, which compress new clouds, which birth new stars, and so on. It's a cosmic chain reaction, not unlike a forest fire that leaves fertile soil in its wake. But with stars, what rises is not just new life, but new possibilities. This feedback cycle plays a crucial role in galactic evolution. Without it, galaxies like Triangulum might have exhausted their star-forming materials long ago. Instead, they recycle, rejuvenate, and regenerate. Triggered star formation ensures that galaxies stay dynamic, that they grow, that they evolve. It also means that our own Sun and Earth may owe their existence to a supernova billions of years ago. Studies of ancient isotopes in meteorites suggest that a nearby supernova explosion occurred just before our solar system formed, enriching the cloud that became the Sun with short-lived radioactive elements. In other words, we are literally made of stardust. And the star that helped make us may have died to give us life. That's not just poetic, it's scientific fact. So when we gaze into the spiral arms of Triangulum, and we see the glowing tendrils of new star clusters wrapped in clouds of pink and blue, we're not just looking at stars, we're looking at a story, a cycle, a legacy of cosmic rebirth that has played out for billions of years and will continue for billions more. And at the center of that story is a simple truth. From death comes life. In the most literal sense, the stars that explode become the stars that shine. Beyond the glowing arms of the Triangulum Galaxy lies a vast, silent structure. Not a disk, not a sphere, but a halo. A dark, diffuse shell of matter that extends tens of thousands of light-years beyond the visible edge. Inside this halo, strange rivers of gas drift quietly, almost invisible to ordinary telescopes. These gas streams may be the remnants of ancient accretion events, when Triangulum fed on smaller galaxies or siphoned material from the surrounding cosmic web. The cosmic web, that immense filamentary structure that connects all galaxies like strands of a universal nervous system, isn't just theoretical. It's real, and it's feeding the galaxy. These streams act as lifelines, channeling matter across millions of light-years and delivering it straight into the gravitational heart of Triangulum. Some of the gas falls into the disk, replenishing star-forming material. Some is captured in the halo, suspended for eons before slowly raining inward. Without this cosmic fuel delivery, the galaxy would gradually run out of the gas needed to create new stars. These inflowing streams are like veins, pulsing with cold hydrogen and other raw materials essential for stellar birth. And even more fascinating, they may carry with them chemical fingerprints from other galaxies, or even primordial matter left over from the early universe. The dark matter halo plays a crucial role here. It doesn't just surround the galaxy, it shields it. Acting like a gravitational net, it can deflect or absorb high-velocity intergalactic gas clouds that might otherwise smash into Triangulum and disrupt its structure. In this way, the halo is both protector and provider. It absorbs some shocks and channels in new resources. This dual function is essential to galactic survival. Galaxies that lack stable halos often suffer from disrupted disks, irregular shapes, or chaotic star formation histories. Triangulum, with its beautifully symmetric spiral structure, owes part of its elegance and stability to the hidden hand of its dark matter halo. But these halos are not featureless. New observations using quasar absorption lines, radio surveys, and X-ray imaging reveal that galactic halos are filled with turbulent flows, cooling clumps, and shock fronts. They're more like stormy atmospheres than calm voids. Some of the most energetic interactions in the galaxy happen not in the core, but in the halo. This changes our entire view of how galaxies work. For centuries, we believed that the visible disk, the stars and arms and bright nebulae, held the secrets of galactic evolution. But now we understand that what we see is only the bright center of a much larger, darker, and more dynamic structure. It's like looking at the glowing coal in the center of a campfire and realizing that the real heat, the energy, the turbulence, the transformation is in the invisible air all around it. This idea has led to a radical shift in astronomy. We now think of galaxies as multi-layered systems, with the disk merely the surface expression of a much deeper gravitational entity. And that entity, the dark halo, may even determine a galaxy's fate. How big it becomes, how fast it spins, how long it lives. The Triangulum Galaxy is no exception. Its beautifully ordered spiral, its star-forming regions, its relatively undisturbed disk, all these may be shaped and sustained by the halo and the gas filaments streaming in from the universe beyond. In essence, Triangulum is not isolated. It is part of a larger ecosystem drawing nourishment from the cosmos itself. And that nourishment doesn't just build stars. It builds worlds. It feeds the engines of planetary systems, sows the seeds of atmosphere and ocean, and creates the chemical foundation for life. So when we talk about the cosmic web, we're not just talking about structure. We're talking about connection between galaxies, between elements, and perhaps, in time, between civilizations. It's a vision of the universe as interwoven, a grand tapestry of gravity, gas, and time. And at the heart of it, galaxies like Triangulum don't merely sit and shine. They reach out, they gather, they grow. Imagine a galaxy not as a static map of stars, but as a living, breathing organism pulsing with cycles of birth and transformation. In the Triangulum Galaxy, these cycles manifest as waves of star formation, vast fronts of stellar birth that sweep across the spiral arms like wildfires in a cosmic forest. These waves are not random. They are triggered by a complex interplay of gravity, motion, pressure, and magnetism. As Triangulum rotates, different sections of its disk pass through compression zones, regions where gas clouds are squeezed by gravitational perturbations. These compressions collapse molecular clouds, leading to bursts of star formation. Some of this comes from internal mechanics, the spiral density waves that act like traffic jams in the galactic highway, bunching up matter and triggering collapses. But other drivers are external. One of the most fascinating is the galaxy's interaction with the cosmic web. As Triangulum moves through this vast, large-scale structure of dark matter and intergalactic gas, it encounters filaments, invisible rivers of gas that fall into the galactic halo and disk. When these cosmic streams rain into the disk, they can shock the gas already present, creating localized starbursts, sudden, intense waves of star formation. Astronomers call this cosmic rainfall, and it may be one of the galaxy's main methods of replenishing its stellar nurseries. But that's not all. Another subtle but powerful influence is magnetism. The magnetic field of a galaxy may seem invisible and mysterious, but it plays a critical regulatory role. Magnetic fields can support gas clouds against gravitational collapse, holding them up like scaffolding in space. This prevents premature star formation. Only when magnetic pressure is disrupted by turbulence or reconnection events do the clouds collapse, creating an oscillating pattern of star birth across different regions of the galaxy. It's like a breathing cycle. Build up, release, hold, collapse. These feedback-driven cycles give the galaxy a rhythmic heart, beating in million-year intervals. Internal feedback mechanisms are also at play. Young stars, once born, emit intense radiation and stellar winds. These push away surrounding gas, halting further star formation in that region, while possibly triggering new stars on the edges of the bubble. This creates expanding shells of starbirth, like ripples in a pond. And then there are the supernovae, the grand finales of massive stars. Their explosive shockwaves both destroy and create, sweeping through the interstellar medium and collapsing clouds farther out. All of this combines into a self-regulating, galaxy-wide engine of creation. Sometimes it speeds up, sometimes it quiets down, but it never stops. These cycles are written into the very structure of the galaxy. In regions where the arms are tightly wound, we find denser waves of star formation. In outer arms or less compressed areas, the process is slower, more diffuse. Even the rotation speed of the galaxy plays a role. Faster rotating galaxies tend to have stronger density waves and thus more pronounced cycles. The position of Triangulum in the local group may also impact these rhythms. Gravitational interactions with nearby galaxies, like the Andromeda Galaxy, can cause tidal effects. These can disturb the disk, stir up gas, and kickstart new waves of stellar creation. In some models, these effects act like a cosmic metronome, syncing star formation with large-scale galactic motion. And there's another tantalizing mystery. Could these waves of star formation influence planetary formation as well? After all, when star formation spikes, so does planet formation, and possibly the emergence of conditions for life. Some scientists speculate that entire habitable epochs may be tied to these galactic rhythms, periods when many new stars and planets emerge together, increasing the chances of life-sustaining environments. This takes us to a stunning realization. The cycles of star formation may not just shape galaxies. They may shape destinies. In the Triangulum Galaxy, we are witnessing a symphony of gravity, light, and time. A cosmic music composed by the universe itself, where each note is a star, each movement a burst of creation, and each silence a preparation for the next crescendo. Understanding these cycles means understanding how galaxies evolve, how stars are born, how planets come to be, and ultimately, how we got here. Because what happens in Triangulum is also what once happened in the Milky Way. Our sun was born in such a wave. Our Earth formed in its aftermath, and somewhere in Triangulum. Right now, a similar wave may be shaping another Earth, another sunrise, another chance. The story of stars is also the story of elements, and the story of elements is the story of life itself. In the early universe, there were only a few ingredients: hydrogen, helium, and a whisper of lithium. But everything else, the oxygen in your breath, the calcium in your bones, the iron in your blood, was forged inside stars. This transformation is known as stellar nucleosynthesis, and it reshaped the galaxy forever. The first stars, called Population 3 stars, were massive, short-lived, and metal-poor. They exploded quickly, creating the first batch of heavy elements: carbon, oxygen, nitrogen, and more. With each generation, the galaxy became richer in metals, a process astronomers call metallicity enrichment. Why does this matter? Because planets, especially rocky, Earth-like planets, can't form in a metal-free galaxy. You need silicon to build crusts, iron to form cores, carbon to create organic molecules. No metals, no Earths. So the journey from a sterile universe to one filled with potential life begins with this slow accumulation of stellar ashes. As stars die, especially in supernovae, they seed the galaxy with these critical materials. But not evenly. Supernova explosions eject metals in powerful winds that rise above the galactic plane, creating enormous bubbles of hot, enriched gas. These bubbles escape the disk temporarily, mixing in the halo, only to cool down and fall back later, in what scientists call a galactic fountain. These fountains ensure that metals don't stay local. Instead, they're distributed across vast regions, enriching the galaxy from core to edge. It's a form of galactic respiration. Stars breathe out their last breath in explosions, and the galaxy inhales their elements to make new stars, new worlds. This mixing process also explains metallicity gradients, the fact that inner regions of galaxies tend to be more metal-rich, while the outer disk remains poorer. Triangulum shows this pattern clearly. At its core, older stars, rich in metals. Toward the edges, younger, less enriched systems. But that pattern is always evolving, shaped by stellar migration, gas inflows, and the fountain-like redistribution of heavy elements. It's also worth noting that metallicity doesn't just affect planet formation. It influences the stars themselves. Molecular clouds with higher metallicity cool more efficiently, allowing them to collapse faster and form stars more readily. However, they also tend to form more low-mass stars than massive ones. That changes the shape of the initial mass function, which in turn affects the entire evolution of the galaxy. Fewer massive stars mean fewer supernovae, less feedback, and slower chemical enrichment in the next cycle. So, metallicity is not just a byproduct of stars. It's a driver of what kind of stars get made next. It's a loop. Stars create metals. Metals shape the next stars. Those stars create more metals, and so on. This elegant feedback loop is what makes galaxies complex and dynamic, and it's what allows life-friendly environments to emerge. Consider this. Earth formed from a second or third generation star. Its crust is filled with radioactive elements like uranium, created in supernovae or neutron star mergers. These elements power plate tectonics, regulate the carbon cycle, and help maintain habitability over billions of years. Without metals, Earth wouldn't just lack a solid surface, it would lack the processes that make it habitable. So when astronomers study metallicity in galaxies like Triangulum, they're not just measuring star stuff, they're measuring the potential for life. Which regions are ready to host rocky planets? Which clouds are rich enough in metals to form Earth-like systems? Which galactic environments are too primitive, still stuck in the hydrogen-helium phase of cosmic history? These are not abstract questions. They guide our search for exoplanets, our understanding of cosmic history, and our place in the universe. In Triangulum, astronomers have mapped the metallicity of different regions using spectroscopy. By analyzing the light from stars and gas, they can decode the elemental fingerprints of these regions, a process not unlike reading tree rings to learn about Earth's climate. The data reveals a turbulent, evolving galaxy, one that is gradually becoming more fertile, more complex, and more likely to host life-bearing worlds. And so the story continues. Each generation of stars builds on the ashes of the last. Each cycle of supernovae spreads the seeds wider. And somewhere out there, perhaps right now, a cloud enriched by ancient stars is collapsing into a solar system, with a rocky planet, with oceans, with life. All made possible because of one thing: the metals of the stars. In the vastness of cosmic time, even galaxies are destined to meet their fate. And one of the most spectacular events in the history of our local group is already underway. A three-way collision between the Milky Way, Andromeda, and the Triangulum Galaxy. This is not science fiction, it's a celestial certainty. The first signs began billions of years ago, with subtle gravitational tugs between Andromeda and the Milky Way. These spiral giants, both brimming with hundreds of billions of stars, were never truly isolated. Locked in each other's gravitational embrace, they've been slowly drawing closer, defying the expansion of the universe. Today, we know that Andromeda is approaching at over 110 kilometers per second. That's roughly the width of Earth's orbit every year. On human timescales, that may sound slow, but in galactic terms, it's a headlong rush. The galaxies are expected to collide in about 4.5 billion years, sooner than our Sun runs out of fuel. For any future civilizations still orbiting stars in either galaxy, it will be a breathtaking spectacle. Giant tidal arms of stars will be pulled outward like cosmic ribbons. Massive bursts of star formation will ignite as gas clouds compress during the encounter. The night skies will bloom with millions of new suns, far brighter and denser than anything seen today. And what's more, Triangulum won't be a bystander. This smaller, elegant spiral galaxy is also moving toward the merger site and may either collide beforehand or be drawn into the aftermath. It could even orbit the newly formed megagalaxy, perhaps merging in a second stage. Some simulations suggest that Triangulum might have already passed through Andromeda once, creating tidal disruptions and influencing both galaxies' shapes. This makes the coming event not just a binary collision, but a triple encounter, one that will forever reshape our cosmic neighborhood. But let's clear up a common misconception. Even though galaxies are filled with stars, space is so vast that collisions between stars are rare. Instead, it's the gravitational fields, gas clouds, and dark matter halos that clash and merge. These interactions will trigger supernovae, starburst regions, gas outflows, and fountains, and possibly the formation of a new supermassive black hole at the center of the merged galaxy. Scientists predict that the final result will be a giant elliptical galaxy, larger and more massive than either Milky Way or Andromeda alone. Its name? Some propose Milkomeda, others M31-way, but its impact will go far beyond naming. For Triangulum, the stakes are high. Depending on its timing, it could be swallowed whole by the merged galaxy, flung outward into intergalactic space, or torn apart, becoming tidal streams wrapped around the new core. Its fate lies in the complex ballet of gravitational forces, a ballet playing out over billions of years. But even now, astronomers can simulate it. Using data from the Hubble Space Telescope, Gaia, and radio observatories, scientists model the velocities, masses, and trajectories of all three galaxies. These simulations are like time machines, giving us a preview of a future none of us will live to see, but one written in the stars. There's even a poetic irony here. The universe began with a rapid expansion, the Big Bang. But in this corner of space, galaxies are now coming together, merging, creating unity out of separation. And while it may seem like an apocalypse, it's really just transformation. Life, if it survives this far in the future, may not fear the merger. It may thrive in it. New stars, new planets, new possibilities. In that sense, this triple galactic collision is not a destructive end, but a grand beginning. A new galaxy will rise, forged in the fires of gravity, shaped by time, and perhaps one day, explored by the beings it helped create. So as we gaze out toward Andromeda in the night sky, a faint blur with the naked eye, we are not just seeing a galaxy, we are seeing our future, a future written in motion, a destiny of stars. Look closely around any large spiral galaxy, and you'll find a swarm of smaller companions, satellite galaxies, orbiting like moons around a planet. The Triangulum Galaxy is no exception. Though smaller than Andromeda or the Milky Way, Triangulum hosts several such satellites. and their influence is far greater than their size suggests. These satellites don't just orbit quietly. They are active participants in the evolution of the main galaxy. One of the clearest signs of this are the tidal streams, long, ghostly trails of stars stretching out across space. These streams are the shredded remains of dwarf galaxies, torn apart by the gravitational forces of their larger host. It's a slow, majestic disassembly, a cosmic cannibalism that takes billions of years. As these smaller galaxies pass through the outer halo of Triangulum, they experience tidal disruption. Stars are stripped from their edges and flung into long arcs, while their dark matter cores, heavier and more resilient, may survive longer, orbiting deep within the galactic halo. These disrupted stars don't vanish. They become part of Triangulum's extended stellar halo, expanding its reach, enriching its chemistry, and preserving a fossil record of galactic history. By studying these streams, astronomers can trace back the interactions that built the galaxy. Each one tells a story of collision, merger, or gravitational entrapment. But satellites don't just lose stars, they change the galaxy they orbit. As they move through the halo, their gravity tugs on the larger galaxy's disk. These gravitational resonances can heat the disk, make it thicker, and even reorganize the spiral arms. In some cases, they trigger waves of star formation by disturbing gas clouds. It's like a child splashing in a pond. The ripples spread outward, reshaping the surface. Over time, multiple satellite interactions can create a flared disk, warp the spiral arms, and leave long-lasting marks on the galactic structure. Triangulum, though elegant, is not static. Its past is written in the scars of these interactions. And its future may include more mergers, more tidal streams, and perhaps the absorption of satellites entirely. But it's not all destruction. Satellite galaxies are also cradles of star formation. Many of them are rich in gas and form stars at a surprising rate. When they merge with Triangulum, they contribute not just stars, but fresh gas, the fuel for new stellar generations. This rejuvenates the main galaxy, keeping the cycle of starbirth alive. Some astronomers even propose that satellites act as timing mechanisms, delivering gas or inducing turbulence at the right moment to regulate the galaxy's growth. There's also a chemical story here. Satellite galaxies often have different metallicities, reflecting isolated evolution. When they merge or are stripped, they inject new chemical signatures into the halo, creating a layered history of enrichment. Like rings in a tree or strata in a canyon, these chemical layers help scientists date the major events in a galaxy's life. In essence, Triangulum is not a lone builder. It is a collaborative architect, assembling itself from a mosaic of past companions. Each satellite, whether consumed, distorted, or still intact, adds to the tapestry. Modern astronomy now recognizes these satellites not as minor curiosities, but as essential actors in galactic evolution. The Milky Way shows the same patterns. Sagittarius, the Magellanic Clouds, and others, all influencing the shape and activity of our galaxy. And so does Andromeda. It appears that no large galaxy is self-made. All are built, in part, by their cosmic communities. The study of satellite galaxies has blossomed with missions like Gaia, Hubble, and soon, the Nancy Grace Roman Space Telescope. They help us see not only the positions of stars, but their motions, histories, and origins. In Triangulum, satellite remnants are beginning to be identified and mapped, piecing together a forensic reconstruction of its assembly. One day, we may have a complete family tree of Triangulum's past companions. A map of every dwarf galaxy it consumed, every stream it created, every flare it endured. Until then, each faint trace of stars beyond its disk is a whisper from the past, a reminder that even the smallest players can leave galactic-scale footprints. and that the universe is shaped not only by giants, but by the countless tiny forces that dance around them. Space is not silent. Beneath the silence of the void, the universe vibrates with gravitational waves, ripples in space-time, produced by cataclysmic cosmic events. These waves were predicted by Einstein over a century ago, but only recently. Thanks to instruments like LIGO and Virgo, have we been able to hear them. And now, with space-based detectors like LISA on the horizon, the next frontier is opening. The detection of gravitational waves not just from our galaxy, but from galaxies like Triangulum. Imagine this. Two black holes spiral toward each other, locked in a death dance. As they merge, they release more energy in a few seconds than all the stars in the galaxy combined, not as light, but as gravitational waves. These waves stretch and squeeze space-time as they travel, imperceptible to us, but measurable by incredibly sensitive detectors. Triangulum, with its rich population of stars, black holes, neutron stars, and binary systems, is likely a constant source of such signals. In fact, some of the gravitational waves we detect today may have originated millions of light-years away, from within its spiral arms. Even white dwarf binaries, far more common than black hole mergers, produce steady gravitational wave hums that LISA is expected to detect. Scientists are preparing to map the gravitational landscape of the entire universe, identifying the exact locations of binary systems, black hole pairs, and merging neutron stars, including those in Triangulum. These observations will allow astronomers to track the evolution of stellar remnants, measure cosmic distances, and even test fundamental physics. But there's more. The universe has been ringing with gravitational waves since the beginning. Some theories suggest a background hum of these waves has persisted from the early universe, created by inflationary expansion, cosmic string oscillations, or early black hole formations. These primordial waves, combined with those from galaxies like Triangulum, form a gravitational wave background, like the cosmic microwave background, but in space-time. And while individual waves are extremely weak, the cumulative effect across billions of years could subtly shape galactic evolution. For instance, some simulations suggest that gravitational wave radiation might influence the migration of planets in binary star systems, alter asteroid belt structures, or even modify comet cloud dynamics. These effects are tiny, but over cosmic timescales, they might become significant. Imagine entire planetary systems slowly shifting their orbits, not from nearby stars, but from waves rippling through space-time itself. The power of gravitational waves lies not just in their violence, but in their reach. They travel unhindered across the universe, unblocked by gas, dust, or light. They carry information from regions we cannot see, such as the interiors of black holes or the moment of cosmic birth. When we listen to these waves, we are not just hearing collisions, we are hearing history. And the galaxies like Triangulum become orchestras, playing out symphonies of creation and destruction across time. What's even more astonishing is how gravitational waves let us see the invisible. Many black holes and neutron stars are completely dark. They emit no light, no X-rays, nothing detectable by traditional telescopes. But when they merge, they produce a burst of gravitational energy that we can now measure. In that moment, they go from invisible to indelible. Triangulum likely contains hundreds, perhaps thousands, of such hidden binaries, waiting to reveal their presence through these space-time echoes. Over time, this could revolutionize our map of the galaxy, no longer built just from stars and gas, but from ripples and reverberations. In the near future, gravitational wave observatories will be able to detect every white dwarf binary in the Milky Way, track massive black hole mergers across the observable universe, and reconstruct galactic events that left no optical trace. These instruments, orbiting silently in space, will act like space-time microphones, tuned to the faintest tremors of the cosmos. Already, collaborations between gravitational wave data and traditional astronomy have led to multi-messenger discoveries. In 2017, for the first time, scientists detected both gravitational waves and light from the merger of two neutron stars. It was a landmark moment, showing how these waves are complementary to light-based astronomy. In the Triangulum Galaxy, a similar event could happen tomorrow, or it may have happened millions of years ago and its waves are just now reaching us. Every gravitational wave we detect from that distance is a time capsule, a message from the ancient past. And as detection technology improves, we'll uncover not just rare events, but a constant background of galactic activity, the living pulse of the universe. It's fitting, then, that Triangulum, a quiet, unassuming galaxy to the naked eye, may be shouting across the cosmos in a language we've only just learned to hear. A language not of light, but of motion. A language etched in the curvature of space-time. A language that, once deciphered, will rewrite everything we know about how galaxies live, die, and dance. It's the most profound mystery in all of cosmology, an invisible force that makes up nearly 70% of the universe, and yet we have no idea what it is. It doesn't clump like matter. It doesn't glow, absorb, or scatter light. It's simply there, pushing, stretching, accelerating the cosmos. We call it dark energy, and it might be the key to understanding how the universe will end. The first clue came from an unexpected place: exploding stars. In the late 1990s, two independent teams of astronomers used type Ia supernovae to measure cosmic distances. These supernovae are known as standard candles. Their intrinsic brightness is so predictable that any difference in observed brightness tells us how far away they are. But what astronomers found shocked the world. The most distant supernovae weren't as bright as they should have been. They were fainter, meaning farther away than expected. The universe wasn't just expanding, it was accelerating. Something was pushing galaxies apart, faster and faster. As time went on, that something was dubbed dark energy. But what is it? One idea is the cosmological constant, first introduced, then rejected, by Albert Einstein. According to this idea, empty space itself has an inherent energy, a built-in pressure that pushes outward. But if this is true, the value must be incredibly small, many orders of magnitude smaller than what quantum field theory predicts. Another idea is that dark energy is dynamic, a changing field called quintessence, which varies over time and space. Yet another possibility, that our theory of gravity itself is incomplete. Perhaps what looks like acceleration is really the sign of new physics, a deeper understanding of space-time we haven't yet unlocked. Dark energy challenges our most fundamental assumptions about the cosmos. It's not just a mystery of matter, it's a mystery of existence. We know that it affects the large-scale structure of the universe. Without it, the mutual gravitational attraction of galaxies would slow down cosmic expansion over time. Instead, the opposite is happening. As dark energy dominates, galaxies are accelerating away from one another, leading to what some call the cosmic runaway. Eventually, this might result in a state where distant galaxies are moving away faster than the speed of light, not violating physics, but being carried by the expansion of space itself. If this continues, we may reach a future where everything beyond our local group disappears from view. A universe where the sky grows darker and emptier forever. But some theories go even further. They suggest a scenario called the Big Rip, where dark energy becomes so dominant that it tears apart galaxies, stars, planets, even atoms. This isn't science fiction. It's a mathematically possible endgame. But we're not there yet. Today, scientists are working tirelessly to measure dark energy more precisely. Missions like Euclid, the Nancy Grace Roman Space Telescope, and the Dark Energy Spectroscopic Instrument, DESI, aim to map the geometry of the universe, track galaxy clustering, and test expansion rates across cosmic time. These tools allow us to build a kind of cosmic history book, showing when and how dark energy began to dominate. If we can measure how it evolves, if it changes over time, we might finally distinguish between theories, and perhaps discover whether the cosmos is headed for a slow fade or a dramatic finale. The Triangulum Galaxy, like every other galaxy in the universe, is a participant in this vast expansion. Its light may one day fade into invisibility, not because it died, but because the universe pushed it beyond reach. Even now, it's part of the silent contest between gravity and dark energy. Gravity pulls inward. Dark energy pushes outward. The future of the cosmos depends on which force wins. And remarkably, it seems dark energy already has. That raises deep questions. Is dark energy a property of space itself? Is it connected to the vacuum energy predicted by quantum mechanics? Or is it something entirely unknown, a fifth force? Could it change, disappear, reverse? These aren't just mathematical puzzles. They are questions about our fate. Will the stars continue to shine forever? Will galaxies remain visible to each other? Or are we living in a brief window of cosmic clarity, soon to be isolated by an accelerating universe? Every time we measure a supernova, every time we chart a galaxy, every time we test the shape of space, we're not just studying physics. We're trying to understand what kind of story the universe is telling. A story with a beginning, a middle, and one day, an end. And in that story, dark energy might be the final chapter, or the key to a sequel we cannot yet imagine. The spiral arms of galaxies are among the most beautiful and iconic structures in the cosmos. They evoke the elegance of order, sweeping arcs of stars, dust, and gas, gracefully winding around a glowing core. But beneath that beauty lies a mystery. How do spiral arms form, and why do they persist for billions of years? The Triangulum Galaxy, also known as M33, offers a fascinating case study. Unlike galaxies with rigid symmetrical patterns, Triangulum shows a complex, asymmetric spiral structure, with arms of varying length, thickness, and brightness. What creates such a pattern? The leading theory is the density wave model, which suggests spiral arms are not made of fixed stars, but rather moving waves of increased density, like traffic jams in space. As stars and gas orbit the galactic center, they slow down when entering a spiral arm and speed up when leaving, creating the illusion of a rotating arm. But Triangulum challenges the simplicity of this model. It seems to have multiple spiral wave patterns operating at once, with different pitch angles and rotation speeds. In other words, it's not a single melody, but a symphony of overlapping rhythms. Some arm segments move faster, others slower. Some wind tightly, others loosely. This suggests that spiral structure is dynamic, constantly evolving. Recent computer simulations show that internal instabilities, such as local gas compressions or turbulence in the disk, can also generate spiral patterns. These instabilities may fade and reform, creating temporary arms or arm segments that appear and vanish over time. In addition, the passage of massive gas clouds, satellite galaxies, or even dark matter clumps can disrupt the regular spiral and create kinks, spurs, or new arms. In some galaxies, a central stellar bar plays a key role in spiral formation, acting like a lever that drives density waves outward. But Triangulum lacks a strong central bar, setting it apart from barred spirals like the Milky Way. So what maintains its graceful swirls? One possibility is that local gravitational resonances, regions where orbital speeds match wave speeds, reinforce the pattern over time. Another is that feedback from star formation, such as supernova shocks and stellar winds, reshapes the surrounding gas and maintains spiral symmetry. It's also possible that the dark matter halo surrounding Triangulum plays a subtle role. Its gravitational influence may stabilize or destabilize certain regions, guiding the overall form of the spiral. This dance of arms is not just aesthetic, it's essential to galactic life. Spiral arms are stellar nurseries, where gas is compressed, cooled, and turned into stars. The most massive and luminous stars are found along these arms, lighting up the structure like cosmic lanterns. Yet these stars live short lives, just a few million years, before exploding as supernovae, feeding energy back into the arms. This feedback process regulates star formation, balances gas pressure, and may even sustain the spiral wave itself. In Triangulum, the star formation rate is high relative to its mass, indicating that its arms are active and vibrant. Observations from telescopes like Hubble, Spitzer, and the James Webb Space Telescope are helping to map these regions in unprecedented detail, revealing how stars, dust, and molecular gas interact across spiral lanes. These insights show us that no two arms are alike. Some contain large, giant molecular clouds, while others are rich in older stars. Some spiral arms branch or split, like rivers forming deltas. Others twist sharply or fade into wisps. This complexity suggests a chaotic elegance, a structure built by order, but shaped by turbulence and time. And as Triangulum rotates over hundreds of millions of years, its arms are rewritten again and again, each rotation painting a new chapter in its spiral history. What we see today is only a snapshot, one frame in a cosmic movie that stretches billions of years. In the far future, Triangulum may develop new spiral arms, lose old ones, or even transform into a different galaxy type altogether, especially after potential mergers. But for now, its spiral pattern continues to mesmerize, a galactic fingerprint of forces we are only beginning to understand. The dance of the arms is more than motion. It's the rhythm of creation. Imagine being able to listen to the afterglow of the Big Bang. That's precisely what the cosmic microwave background, CMB, allows us to do. It's not just radiation. It's a snapshot of the universe when it was only 380,000 years old. Long before galaxies formed, before stars ignited, the universe was a hot, dense soup of particles and radiation. As it expanded and cooled, protons and electrons combined into neutral hydrogen atoms. In that moment, light was finally able to travel freely. And that light is still traveling today, stretched by cosmic expansion into microwaves. This ancient radiation now bathes the entire cosmos at a temperature of just 2.7 Kelvin, barely above absolute zero. But despite its faintness, the CMB holds extraordinary power. It is the oldest light in the universe, and it maps the subtle density fluctuations, ripples in the early universe, that later grew into galaxies, stars, and planetary systems. These tiny variations in temperature and polarization are the seeds of all cosmic structure. Without them, the universe would be a featureless fog. Today, the CMB serves as a cosmic backdrop, a standard reference against which all motion and structure can be compared. In fact, it defines a kind of universal rest frame. By observing how galaxies and spacecraft move relative to the CMB, scientists can measure true motion through space, not just relative to nearby stars. More importantly, the CMB provides a baseline for measuring cosmic expansion. It gives us insight into how quickly the universe is accelerating, and therefore into the effects of dark energy. But the CMB is not static. As galaxies evolve, their hot gas interacts with the CMB through a process called inverse Compton scattering. This happens when fast-moving electrons, typically found in galaxy clusters, collide with microwave photons, boosting them to higher energy levels. The result? Slight temperature increases in localized areas of the sky. These thermal distortions help astronomers map the distribution of hot gas across the cosmos and track the formation of galaxy clusters. In other words, the CMB isn't just a relic of the past, it's still actively shaped by the universe today. Precision measurements from missions like COBE, WMAP, and Planck have allowed us to detect these interactions with stunning clarity. These missions revealed a universe that is flat, homogeneous, and governed by dark energy and dark matter. They also gave us exact numbers. The universe is 13.8 billion years old, composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. But here's the irony. As the universe continues to expand, the CMB is fading, its temperature is dropping, its wavelength is stretching, and one day, it will become so redshifted that even our most sensitive instruments may no longer detect it. Future civilizations, billions of years from now, may live in a universe where the CMB is completely invisible. They may have no direct evidence of the Big Bang, no knowledge of early structure, no access to the deepest origin of time. That's why our time is unique. We exist in an era where the CMB is still visible, still readable. A cosmic relic that allows us to study the past, map the present, and even predict the future. By analyzing its polarization patterns, scientists are also hunting for something even more elusive: primordial gravitational waves, ripples in space-time from the moment of inflation. If found, they would be the final piece of evidence for the inflationary model of the early universe. Triangulum, like all galaxies, formed long after the CMB was released, but the CMB still permeates the space around it. It is part of the cosmic weather that all galaxies experience, a silent, omnipresent hum from a time before time. Some researchers believe subtle CMB interactions may even play roles in fine-scale galaxy formation, especially in the early universe. In this way, the CMB is not just an echo, it is an active participant in cosmic evolution. As we look deeper into the fabric of the cosmos, we come to understand that light, even ancient light, still speaks. And the CMB speaks with the voice of creation itself. From the smallest particles to the largest structures, the universe is shaped by quantum whispers. In the earliest instant after the Big Bang, the universe was governed not by stars and galaxies, but by quantum fluctuations, brief, random variations in energy. These tiny differences were amplified during cosmic inflation, stretching quantum imprints across unimaginable scales. Over billions of years, those fluctuations grew into the cosmic web, the vast, filamentary structure that defines the universe today. When we observe the Triangulum Galaxy, we're not just seeing a spiral of stars. We're seeing a node in a much larger tapestry, one stitched together by dark matter and shaped by quantum chance. The galaxies we observe, including Triangulum, tend to form along these filaments of invisible matter, interconnected like the threads of a cosmic spiderweb. Between these filaments lie cosmic voids, vast, empty regions stretching millions of light-years across. And yet all of this, every galaxy cluster, every glowing star, originated from tiny ripples in the early universe. These ripples, born of quantum uncertainty, determined where matter would gather and where it would not. It's a staggering thought that the shape of the universe on the largest scales is dictated by laws that govern the tiniest particles. The clustering of galaxies, the distribution of dark matter, even the voids between stars, all are statistical expressions of those first quantum fluctuations. In this sense, the cosmos is not a chaotic explosion, but a precise unfolding of probabilities. Triangulum's place in the universe was determined not by chance, but by quantum law. The same laws that dictate electron orbits and photon behavior also govern where galaxies form, how they move, and how they connect. The cosmic web is not visible to the eye, but its effects are unmistakable. Galaxies do not distribute randomly. They form clusters, walls, and filaments. The Triangulum Galaxy belongs to the local group, which itself is embedded in a filament of the Laniakea supercluster. That filament curves through space, connecting Milky Way, Andromeda, and hundreds of other galaxies in a delicate gravitational balance. And the invisible glue holding it together? Dark matter. Though we cannot see it, dark matter is the scaffold of the cosmos, providing the framework on which ordinary matter gathers. It responds to gravity, but not light. It's 5 times more abundant than visible matter, and its distribution was set, in part, by those primordial quantum fluctuations. Simulations of the early universe, such as the Millennium simulation, have shown how these fluctuations evolved into the cosmic web. The resulting maps are eerily similar to what we observe with telescopes. That alignment tells us that quantum physics didn't just shape the microworld, it shaped everything. Triangulum is one point on a billion light-year-long thread of gravity and dark matter. Every star in it, every planet, is part of a larger structure that is itself part of something grander still. This web is not static. It evolves as gravity pulls galaxies closer, as clusters merge, and as dark energy pushes space apart. Over time, the cosmic web becomes more intricate and more stretched. In the distant future, entire filaments may become isolated as dark energy accelerates expansion. Yet the imprint of quantum origin will remain. Every galaxy will still trace the same ancient scaffolding. And perhaps most profoundly, we are a part of that. The atoms in our bodies, forged in stars, arranged into molecules and minds, ultimately follow the same statistical distributions seeded by quantum mechanics. That means we, like Triangulum, are products of uncertainty, not randomness, but structured possibility. From quantum ripples to galaxies to consciousness, a hierarchy of emergence written into the universe from its very first moment. To contemplate the cosmic web is to contemplate our place in the grand scheme. We are not separate from the universe, we are threads within it. The Triangulum Galaxy is not floating in isolation. It is embedded, anchored, and connected to all things by the invisible strands of cosmic geometry. In this web, everything is related. Every fluctuation, every filament, every star. Each plays its part in the orchestra of the cosmos. And in that music, you can still hear the quantum beat of creation. The universe we see today, alive with light, stars, and galaxies, is merely the opening chapter of a much longer story. For the last 13 billion years, we've lived in the stellar era, the age of stars. But even this brilliant phase will one day end. In the Triangulum Galaxy, the cycle of stellar birth and death is already well underway. The most massive stars, those luminous blue giants burning with the intensity of millions of suns, are the first to die. They live fast, burn bright, and vanish young, lasting only a few million years. Some explode in spectacular supernovae, enriching the galaxy with heavy elements. Others collapse directly into black holes, vanishing from view, but leaving behind immense gravitational footprints. These deaths seed the interstellar medium with carbon, oxygen, iron, the raw materials for planets, life, and future stars. Meanwhile, medium-mass stars, like our Sun, live more balanced lives. They burn steadily for billions of years, fusing hydrogen into helium in their cores. When their fuel runs out, they swell into red giants, engulfing nearby planets. Eventually, they shed their outer layers, forming glowing planetary nebulae, leaving behind a small, dense white dwarf core. This white dwarf, no longer undergoing fusion, slowly radiates stored thermal energy, cooling over tens of billions of years, first glowing white-hot, then red, then fading to black dwarfs, cold, dead embers adrift in space. But the most enduring stars of all? Red dwarfs. These low-mass stars, with less than half the mass of the Sun, are cosmic misers, burning their fuel so slowly they can shine for trillions of years. None have died yet. The universe simply isn't old enough. But one day, even these long-lived flames will flicker out. Triangulum is filled with such stars, quiet, stable, and faint. In the far future, when the giants and medium stars are long gone, these red dwarfs will dominate the night sky. They will be the last beacons of visible light. But not forever. As time passes, the galaxy will grow darker. Star formation will cease as gas is exhausted. Existing stars will die out. Triangulum, like all galaxies, will enter a degenerate era, an age defined not by light, but by remnants. White dwarfs, neutron stars, black holes, and cold brown dwarfs will populate a dimming cosmos. A galaxy of ghosts. Occasionally, chance gravitational encounters may spark rare events. A white dwarf colliding with another, reigniting briefly. Or two black holes spiraling inward and merging, sending out a burst of gravitational waves. But such events will become rarer and rarer. Energy will disperse. Motion will slow. Stars will no longer shine. In time, black dwarfs may even undergo theoretical processes like proton decay, dissolving into radiation over unimaginable timeframes. Eventually, only black holes will remain. Triangulum's massive stellar black holes, and perhaps a central supermassive black hole, will continue to warp space around them. But even they are not eternal. Through Hawking radiation, black holes slowly lose mass. Over trillions of years, they too will evaporate. When the last black hole disappears, the universe will enter its final stage, the dark era. No stars, no galaxies, no light. Just a thin mist of particles spread across a frozen cosmos. This is the long twilight of existence. Yet even this future is written in the stars we see today. In Triangulum, the dance of birth and death continues. But it is a countdown. Every new star formed is one step closer to the end of starlight. We live in a brief golden age, a flickering moment in which the universe still glows. Billions of years from now, future civilizations may look up and see only darkness. No Triangulum, no Milky Way, no stars, only memory or legend. That's why this time is precious. The universe is young and alive. And the Triangulum Galaxy, spinning, shining, birthing stars, is a reminder of all that still burns before the long cold begins. We are stardust with a window into eternity, and that window is still open. As the final stars fade and the galaxies go dark, a new era dawns. An age not of light, but of shadows. The universe will enter its black hole era, a time when all that remains are the collapsed remnants of matter, black holes silently ruling the cosmic void. Over trillions upon trillions of years, gravitational interactions will gradually draw matter toward the hearts of galaxies. Stars, gas, planets, even the dark matter halos, all will be consumed or ejected, leaving behind massive black holes as the ultimate survivors. In galaxies like Triangulum, everything once bright and burning will collapse into the central maw. The remaining stellar corpses, white dwarfs, neutron stars, and rogue planets, will spiral inward under the pull of gravity. Tidal forces will stretch and shred them apart before they cross the event horizon, vanishing forever. This is not a violent apocalypse. It's a slow, inevitable process, a gravitational whisper, not a scream. The once glorious galaxies of the universe will be reduced to silent orbs of darkness, each harboring a single supermassive black hole, the final remnant of billions of stars. But here's the profound twist. Even black holes die. According to Stephen Hawking's theoretical calculations, black holes are not truly black. They emit tiny amounts of thermal radiation, known as Hawking radiation, due to quantum effects near their event horizons. Over vast timescales, this radiation causes them to lose mass. A black hole the mass of our Sun would take roughly 1067 years to completely evaporate, a number so large it transcends imagination. And supermassive black holes, like those anchoring galaxies, could persist for 100 and 100 years or more before fading away. In their final stages, they would shrink rapidly, glowing faintly, and then vanish in a flash of radiation. No light, no sound, just gone. After the last black hole has evaporated, the universe will be left with nothing but a thin haze of particles, photons, neutrinos, and perhaps some decayed protons, slowly spreading into a volume that expands forever. This is the dark era, a time with no structure, no energy gradients, no entropy to consume. The universe will approach heat death, a state of maximum entropy where no usable energy remains to perform work. Time, in any meaningful sense, will cease to flow. Nothing will change. Nothing will move. Just stillness. And yet, there's beauty even in this cold silence. The universe will have lived a full life, from quantum spark to majestic galaxies to its quiet unraveling. And in that arc, from fire to frost, it will have created everything. Stars, planets, life, minds. From the Triangulum Galaxy to the farthest quasars, each played its part in this cosmic symphony. Humanity, too, was part of it, a brief flicker of awareness in a sea of stars. We came, we looked, we wondered. And in doing so, we gave the universe a voice. Perhaps that's the most remarkable thing, that something born in the heart of a star could look back at the stars and understand. The death of black holes does not mean defeat. It means completion. Every cycle ends. Every symphony must reach its final note. And the universe, vast, ancient, mysterious, will leave behind a legacy imprinted in the very fabric of existence. That imprint will remain forever, etched in time, though no one may be left to see it. Triangulum, Milky Way, Andromeda, all will dissolve. But their stories were real. Their lights once shined. Their gravity once danced. Their atoms once dreamed. And so we end where we began, in awe, in silence, and in wonder. The final chapter of the universe is not a bang or a blaze, but a soft and graceful bow, a curtain call on eternity. The universe is vast, and within that vastness, galaxies like Triangulum do not exist in isolation. They are strung along a grand cosmic web, a lattice of dark matter filaments that stretches across billions of light years. These filaments guide the flow of gas, galaxies, and gravity itself, echoing the quantum fluctuations from the very birth of the cosmos. It is a structure so immense, so intricate, that even our most powerful computers can only simulate fragments of it. But the more we learn, the more we realize how little we truly know. Every discovery seems to answer one question while raising 10 more. What exactly is dark matter, and why does it outweigh all the visible matter we can detect by more than 5 to 1? What is the true nature of dark energy, and how does it cause the universe to accelerate, expanding faster as it ages? Are black holes really just gravitational traps? Or are they gateways, storing information in ways that challenge our very understanding of physics? And perhaps the greatest mystery of all, are we alone? In this vast cosmic theater, do other forms of consciousness gaze upon the same stars, ponder the same mysteries, and wonder about us as we wonder about them? The search for life in the universe has grown more urgent, as we've come to understand just how complex and diverse galaxies like Triangulum truly are. With hundreds of billions of stars and potentially trillions of planets, it seems unlikely that Earth is the only cradle of life. But where is everyone? This is the paradox that physicist Enrico Fermi famously posed. If intelligent life is common, why haven't we heard from them? Perhaps the answer lies in time. Civilizations may rise and fall like cosmic waves, their signals lost in the vast ocean of interstellar space. Or maybe they watch in silence, waiting for us to reach a certain level of maturity, technologically, ethically, or spiritually. There are theories suggesting advanced life may transition into non-biological forms, uploading consciousness into machines that no longer seek to communicate in ways we'd recognize. Others posit that the very structure of the universe is tuned for life, a principle called cosmic fine-tuning, suggesting intelligence is not a byproduct of evolution, but an inevitable outcome of complexity. In that sense, the universe may be not just a place for life, but a factory of minds. Perhaps consciousness, once sparked, is destined to spread, evolve, and reshape the very cosmos that gave rise to it. This vision reframes galaxies like Triangulum as not just stellar islands, but potential hosts for awareness. Maybe, among its spiral arms, civilizations have already flourished. Maybe they've reached levels of understanding we can't imagine. Maybe they've left behind megastructures or Dyson spheres, star-encompassing machines designed to harness all the energy of a sun. So far, we've found no such signs, but absence of evidence is not evidence of absence. The galaxy is vast, and our search has just begun. With next-generation telescopes like the James Webb Space Telescope, LUVOIR, and HABEX, we are poised to peer into the atmospheres of distant exoplanets. We may soon detect signs of life, oxygen, methane, or perhaps unfamiliar biosignatures, whispering across light years. And if we do, it will be one of the most profound discoveries in human history. Confirmation that we are not alone will change everything. Religion, philosophy, biology, all will be reshaped. But even if we never hear another voice in the void, the search itself has value. It is in asking the question that we define who we are. The Triangulum Galaxy, with its stars, its dust, its swirling structure, is more than just matter. It is a canvas, a stage for evolution, a mirror for our own hopes. And so the journey continues. Through silence, through science, and through the boundless imagination of minds bold enough to ask, what else is out there? Perhaps one day we will find life, or perhaps we are the beginning, the first spark of consciousness in a sleeping universe. If that is so, then our mission is even more sacred, to illuminate, to explore, and to awaken the cosmos.